All right, so today we're going to go ahead and continue with 4.2, which is again on the mean value theorem. So again, this is just part 2. So we're going to go ahead and start with a quick little warm-up problem. So this one is not in your notes, but it just allows us to go ahead and just look at what we talked about yesterday. So let's go ahead and get a function. So let's go ahead and start with this function right here. F of x equal to arc sine. So arc sine of x, so the inverse sine function. And then let's go ahead and consider this on the closed interval -1 to 1. So let's make sure we know what we're looking at. Well, first of all, we have that f is continuous. We have that it is on a closed interval. So closed interval. And again, the other condition that we have for the mean value theorem is that it's going to be differentiable on the interior. So it's differentiable on the interior. So the three conditions for the mean value theorem are satisfied. And remember that the equation associated with it was that f of b minus f of a divided by b minus a is going to be equal to f prime of c, where again, this is b, and then this is what we're trying to find. We're trying to find the point C in the interval where the tangent slope is the same as the secant slope. So again, we're trying to find the point C in the interval, -1 to 1, such that the secant slope is equal to the tangent slope. So they're parallel lines. So in order to go ahead and do that, we could break this into 3 different parts. So we can go ahead and just find f of a, in this case, f of -1. So we have to find arc sine of -1. Let's remember how to compute this. If you look at arc sine, you have to consider one quadrant that is positive-wise and one quadrant that is a negative-wise. So where we're considering essentially the first and the fourth quadrant. Then the y value down here is 0, -1. So therefore, what angle are we looking at? -π/2. And remember that you go counterclockwise, not all the way around. So you're not going to use 3π/2, you're going to use the -π/2. In a similar manner, we compute f of 1, which is arc sine of 1, which is going to be up at the top of this unit circle, so it's π/2. So we've computed f of a and f of b. And recall that the derivative of arc sine does not involve trig functions, but it is the 1 over the square root of 1 minus x squared. So this is the setup to use the mean value theorem. And what we'll go ahead and do now is use this equation, and that'll allow us to find the value of x, or in this case, c, x or c, remember c is just an x value, that satisfies the conditions of the mean value theorem. That is to say, the secant slope is going to be the same as the tangent slope at that point c we find. So let's do that. So we'll have f of b, we computed to be π/2. Let me make the pen size a little bit smaller. So let me zoom in here. We have π/2. So that's f of b minus f of a is minus π/2. And then divide that by 1 minus a minus 1. And then this will be equal to the derivative, which is 1 over the square root of 1 minus x squared. Again, you could go ahead and put c if you want. That's how I believe the view and example will explain it. But again, we're just looking for some value of x. So this will take a few steps, but let's go ahead and through that. So remember that you could think about this right here as 1/2 plus 1/2. If you ignore the pi, it's just going to be 1. So at the top, we have pi. In the denominator, we have 1 minus a minus 1 is going to give us 2. And that will be equal to 1 over the square root of 1 minus x squared. So all I did here was simplify the left-hand side. We will now reciprocate both sides, so we get the x out of the denominator. Again, this is just one way to think about it. So this is going to be 2 over pi, and then it'll be equal to the square root of 1 minus x squared over 1. Of course, anything divided by 1 is 1, or not 1. Anything divided by 1 is whatever the numerator is, so we have that. We will now square both sides. Remembering to square both the numerator and the denominator, you get 4 over pi squared. That will be equal to 1 minus x squared. Again, all I did here was square both sides to get rid of the square root. You could rearrange this a little bit. So what I'm going to go ahead and do is I'm going to add the x squared over, and then I will subtract this fraction to the other side. So we have x squared equal to 1 minus 4 over pi squared. And then lastly, we will take the square root of both sides, and we'll find x is equal to plus or minus the square root of 1 minus 4 over pi squared. Again, this is a little bit nasty. It does work out to be, I think, about 0.9. So it is a value between -1 and 1, so plus or minus 0.9. Don't forget the plus or minus, because whenever you take the square root of both sides, you do consider both the negative and the principal root. So let me temporarily pause the sharing and take questions, or not pause the sharing, pause the recording. So that is how we used the mean value theorem. What we're going to do now is use the mean value theorem to understand the answer to these two questions that we posed at the beginning of 4.2. That is to say, is there some more complicated function who has a derivative that's always 0? We know our constant functions, the derivative is always 0, but what about something more complicated? And then the other question we want to look at is, if two functions have identical derivatives over the interval, how are they related? So let's go ahead and look at the answers to these questions. So we know that a constant function, this is the same thing as that I asked about before, or that I mentioned before. We know that a constant function has a derivative of 0. Again, constant functions are like 2, the derivative of 2 is 0. It may be something like e to the pi, the derivative of e to the pi is 0, because a constant to a constant is 0. But what about something more complicated? And a corollary, again, if you explore more deeper into mathematics, you'll see phrases like corollary. And a corollary is basically something that follows from a theorem. It's not as deep, but it is an interesting result to state. So here's the result. So if the derivative of a function is 0, then that function has to be a constant. So the answer to this question is no. There are not more complicated functions, and we'll go ahead and actually use the idea of the mean value theorem to understand why. So what we want to think about is, why is that the case? Well, let's go ahead and consider this as our function that we want to look at. And let's go ahead and just say, you know what, the derivative is going to be 0. So f of b minus f of a divided by b minus a, that will be equal to 0. Why? Because we're saying, you know what, the derivative is equal to 0. So instead of f prime of c, we're just going to say that, hey, the derivative is 0. Notice if you solve this or let's go ahead and not necessarily solve it, but we're just going to move things around. When we cross multiply, the denominator crosses out. So we have f of b minus f of a. And then this will be equal to 0. So if we go ahead and just consider, what is this saying? That is to say that f of b is equal to f of a for all a and b. And again, a and b, these are x values. So if we're thinking about what is this saying, there is no change in f in the function, regardless of what x values you're looking at. So what are we saying? There's no change. Oh, that literally means that, so f must be the constant function. So this is a very simple proof. And again, when you, if you were to continue in mathematics, you'd understand more of the formality of proving things. But this is kind of the idea. We dealt with complete generality and said, okay, let's suppose the derivative was 0. What is f? Well, because f of a is equal to f of b for all values of a and b, it must be the constant function. So if the derivative is equal to 0, then your original function must be the constant function. Again, this was just a very simple idea of a proof. You won't need to necessarily provide this logic on a test, but again, for those of you going to explore more mathematics, this is kind of a basic idea or basic introduction to how to prove theorems and statements. So the other question we want to go ahead and answer is the question is, if two derivatives are identical, how are the functions related? And honestly, you may have actually noticed this as you've just gone through exercises, and maybe you even noticed it last time when I put a few up on the page. So if two functions have identical derivatives, here's the corollary. So we're saying their two derivatives are the same at each point x in some open interval, then there exists a constant, let's say c, such that the first function is literally just going to differ from the second function by a constant. What does this mean geometrically? Well, you can see this over here. We have, let's say, x squared, and we're going to add a constant or subtract a constant. Well, these are all only differing by a vertical shift. So the addition or subtraction of a constant does not change the derivative. And if we look at this, all of these functions to our right have a derivative of 2x. So here's the answer to how they are related. Well, they're going to be related by just a constant factor. So this is an idea that we'll explore a lot more in Calc 2, but we are going to introduce it here, and then we're also going to spend some time with it on 4.8. And some of the difficulty in Calc 2 comes from the idea that we have to take everything that we did in Calc 1 and we have to do it backwards. So we're going to go ahead and start to think about that a little bit and just a few basic examples. So the takeaway from right here, how are functions, they're related? Well, they're just related by a vertical shift if you're thinking about it geometrically, or you could think about them by they're related by just some constant plus or minus some c. So what we want to go ahead and think about is, suppose we have their derivatives. Suppose we have 2x. What was our original function? So we'll just think backwards to do that. Let me pause the video and just see if there's any questions. So in example 3, we are asked to find f. So again, we don't have f prime here. This is actually asking us to find the original given the derivative whose graph passes through the given point P. So we'll focus on how to use that point here in a few minutes. What we first want to think about is just, what is our original function? And honestly, there's really no shortcut at this point. There's a few of the basics that you really just have to kind of guess and check. So if I'm looking at sine, I at least have some mastery of what are my derivatives for my trig functions. So I may be like, okay, oh, I know sine and cosine go together. So I'm just going to guess. Is my original function, is it cosine of x? And well, I'm going to check it. Well, f prime of this guess would be negative sine of x. So nope, that wasn't correct. But you will get some sort of insight. So what you may do is think about, oh, I'm off by a negative sign. So what if my second guess, I just go ahead and say, what if my second guess was negative cosine of x? So again, this is just kind of, I'm thinking through it backwards. Now I remember there's a negative involved. So again, I'm going to just check this one. F prime of x, when I take the derivative, will be negative a negative sine of x. Oh, that's sine of x. So yeah, that is actually the same as the given derivative. So I have found a function. I have found an original function. But we have to be careful here. So let's go ahead and just take this up here. So f prime, or f of x, our original function, is equal to minus, here, let's make sure I take the right one up. This was my guess. So I want to take up this minus cosine of x. But let's be careful. What did we just learn about how the functions with the same derivative are related? They're related by a constant. So let me go ahead and put that in red so we really pay attention right here. So if we were just asked for a function, well, we need a little bit more information. What we actually have right here is this is defined a class of functions that all differ by a constant. So we can see that's actually what we're looking for in part, this bottom part. But in this top part, what we can go ahead and do is use this given point to go ahead and find an exact function. So remember that this is a point, so this is an x and a y. So let me go ahead and plug this in. When I plug in x, I am equal to y. So this will be 2, will be equal to minus cosine of 0 plus c. When I plug in 0, I am equal to 2. And that so I plugged in 0, I am equal to 2. And therefore, we have 2 equals to, well, remember cosine of 0, we're right here. So cosine of 0 is going to be equal to, let's see, cosine of 0 is equal to, wow, I'm blanking right here. 1, wow. So minus 1 plus c. So what is c? Add 1 to both sides, we find c is equal to 1. C is equal to 3. So we have our final answer is f of x equal to minus cosine of x plus 3. This is the function whose derivative is sine and is passing through this point right here. So let me pause the recording and just give everyone a moment to try B. So let's go through the solution to part B. Part B is a little bit easier because it's just polynomials, and we're essentially just needing to reverse the power function. So just like before, I'm going to just take a guess, and I have some intuition at this point about what derivatives are, and I feel like that 2 came down from the power. So my guess is going to be x squared minus 1, and I've taken the derivative of x several times, so I'm like, oh, the derivative of x is just 1. So this is my guess. And of course, I'm going to check it. F prime of x would then be equal to 2x minus 1, which is the same as my original. But again, remember, this is only one such answer. The actual thing we have to go ahead and consider as our answer is f of x is equal to x squared minus x plus some constant. So again, if we kind of look ahead, the down here, the directions say find all possible functions with the given derivative. Well, that's what we have right here. In the question here, we're asked to go ahead and find the given derivative whose graph passes through the given point P. So because we are given this point P, we have an x and a y value that we could go ahead and plug in. So when I plug in x of 0, I'm going to be equal to 0. So I plug in x, and then I need to be equal to 0. And again, up here, before I put it over here, you could put it over here since we're more natural to seeing something like that. But either way, you put it, or either side you put it on, if you simplify this, you find c is equal to 0. So what is our actual answer here? The one that satisfies having a derivative of 2x minus 1 passing through the point 0, 0? Well, that's going to be f prime, oh, excuse me, that'll be an original function. So f of x will be equal to x squared minus x plus 0, or just this. So let's now look at how to handle the problems at the bottom. So all of the possible functions with the given derivative. So this one will actually have the plus c in the answer. So this one, again, we have some knowledge about how e to the x works. You may just even say, oh, e to the x, I know if there was no constant in there, it would just be e to the x. But of course, we have this chain rule we have to think about a little bit. And for now, the method we're really going to do is just kind of focusing on guessing and testing and adjusting our answer. In Calculus 2, you'll learn something known as integration by substitution. And that's another way to approach this problem. But for now, one thing that you could always think about to make it a little bit easier is just ignore the 3. If you're ignoring the 3, you just remember what happens when you have a constant multiple. You just put it in at the end. So I'm really going to be focusing on the 4x. So I'm going to take a guess. Y, my original function. Well, I'm going to just see what would be the derivative if I didn't mess anything with the chain rule. Let me just recall that. Well, this is my guess. Y prime, or f prime of x, would then be e to the 4x times the derivative of the inner, which is 4. Okay, so that does give me a little bit of insight. This is not the correct answer. This is not the, this function right here is not the original function whose derivative is given. But I do realize that what I need is a 3. So if I put a 3 here, I put a 3 here. And I need something to cancel out the 4. So if I divide this by 4, well, that's again just a constant, so I'm going to divide that by 4. So my new guess, and let's just kind of think through this and see if this is right. So this was wrong, but, well, here, this one was wrong, but let's take a second guess. This time, I'm going to do 3/4 e to the 4x. This is my guess. Let's take the derivative. Y prime would be equal to 3/4 as a constant multiple, so I'm going to leave that out in front. The derivative of e to the 4x is e to the 4x times 4. And notice now that, yeah, this is 3e to the 4x, which is my original derivative. So here we go. I have found an original function whose derivative is as given. But do remember, we want all the possible functions. So y would be equal to 3/4 e to the 4x plus some constant c. Don't forget about me. Ah, that rhymed. So don't forget. I'm not going to lie, probably well, that's a little bit of trauma when I took Calculus 2 and I would forget about the c, and I would lose a point or two. So I'm just going to iterate. Remember, when you're looking for all the possible functions, that you do have that plus a constant. And again, like I said, there's really no shortcut to these, especially the basic ones. You really essentially will have formulas. And again, if you go through Calculus 2, you'll find the whole course, or not the whole course, but I'd say about 3 of the 5 chapters are about this kind of basic idea. So sometimes it does help to rewrite these in terms of functions you're more familiar with. So if I rewrite this one down here below as minus x to the minus 2, then a quick little thinking about it backwards, we have the derivative of x is 1. And then this right here came from a positive x to the minus 1 plus c. And again, this is just the same as x plus 1 over x plus c. We've taken these derivatives quite often, so hopefully you recognize a few of these just from our work so far. So again, don't forget the plus c, but here is our answer. Again, same answer, just different forms depending what I did with the power function. But this is the process of thinking backwards to obtain our original function. So this idea of thinking backwards is actually a special type of problem known as initial value problems. So initial value problems are actually deserve a whole course to themselves. So this would actually be if you were to take differential equations. So this is a very applicable portion of mathematics. This is where you get vector fields. So essentially, if you were thinking about weather models, you know, like when hurricane season comes around, you have all those spaghetti models. And essentially what they're doing is they're looking at the initial position of the hurricane, and they're trying to look at the wind pattern as the rate of change. And that is essentially how they're getting these models, is using different types of differential equations. But again, this is a whole course to itself, just from this one idea. And again, actually, it's multiple courses. You have ordinary differential equations, which deal with just two-dimensional space, and then you have another whole course called partial differential equations, which is typically it's a special topics course or a graduate level course, so it's not offered as its own course, but as a special topics in undergrad usually. But let's go ahead and just get the basic idea of what an initial value problem is. And it's again this idea of, we're given the rate of change, let's find the original function. So you can see right here, we're going to be looking at this in the context of acceleration. So we're given the second derivative. So let's go ahead and say, let's see what we're asked to find. Part A, find the velocity function. So we are given the acceleration, which, remember that acceleration is the second derivative. So in part A, we have the acceleration at time t is a constant, 9.8, and technically meters per second squared. So let's think about this backwards. What would be the velocity function? Recall that the velocity function is the first derivative. And since the acceleration is a constant, it's pretty easy to go ahead and look at this. The velocity would just be 9.8 times t. And of course, this, let's go ahead and verify this is correct. Technically, our velocity function is going to be plus a constant, and we'll kind of look at that afterwards. But you can see right here, even if you have the constant, when you take the derivative of the velocity to get acceleration, you still get 9.8 plus the constant goes to 0. So this is good. But how would we find that constant? Well, again, think about the context right here. We are told that the object falls from rest. So at the starting point, it has no velocity. It was at rest. So it's not like we're looking at a model where we had already thrown it up. So you can see right here, this would immediately, if you're thinking about hurricanes where there's a lot of movement already, you have different initial values. But how would I find C? Well, let's go ahead and use what we were given. We were given V of 0 is equal to 0. So when we plug in 0, we get 9.8 times 0. We're going to be equal to 0. Oh, excuse me. 9.8 times 0 plus the constant is equal to 0. So you can see our constant is C. So what is the answer to A? It's our velocity function. So it's just going to be 9.8 t. No constant, because as we can see, it falls from rest. So the constant went to 0. So for part B, we have to find the object's position. Remember, again, just what is the position function? If you recall, the position function S of t is, let's write it like this. The velocity, oh no, how am I writing this? S prime of t is the velocity. So again, we have the first derivative, we need to get back to the position function. And again, this is one of those that if you're thinking about what happened to get the 9.8, well, the t came from t squared. So like originally we're thinking, oh, there was a square, came down, doubled it. So we have to really think about, oh, how do I get a 9.8 when I take the derivative? I had to start with half that. So again, I'm just going to kind of say, okay, what is my guess for it? Maybe my position function was half of 9.8 t squared. So let's go ahead and and this is, I think, meters. So if we were keeping an eye on our units, so it would be meters. And simplifying this, S of t would be equal to 4.9 t squared meters. And this is technically still just a guess. We haven't verified it. It's technically plus a constant, so plus a constant meters. And when we take the derivative, S prime of t, we do indeed get 9.8 t plus 0 meters per second if we're paying attention to our velocity units. Oh, yeah, that's good. That's what we had right here for our velocity. So of course, just like before, we want to go ahead and consider what were we given. We were given that it started from rest. So up here, we were given S of 0 is equal to 0. So we were given that when you plug in 0 is equal to 0. Now let's plug it in and see what happens. So 4.9 times 0 squared plus a constant is equal to 0. So C is equal to 0. So we have our position function. So S of t would be equal to 4.9 t squared. So we have found the initial value function. And again, why is this important? There's a lot of things in life that we only know are changing. Maybe we want to go back and think like, okay, maybe even in the context of COVID-19, like we now know how many new cases we have in one day. Maybe we want to go back and think about, when did it start? Well, if we know if we have some idea that it's an exponential model, and we know that from yesterday to today, we had so many new cases, an initial value problem would allow you to maybe go back and look at time. When did it start and what was happening? Maybe that's one way that you could look back historically and understand maybe what could have been done better or what could have been done differently in these sort of global phenomena. But that is a quick introduction to the initial value problem. What we will do in the next section will be looking at optimization in the context of the first derivative rule. And that'll allow us to go ahead and kind of look at just where our max and mins, local, global, and so forth. If you have any questions, let me know, but keep up the good work. We have 1 month left.